Hey AP Chemistry, it's Miss Gray again, and now we're starting Unit 6, which is all about atoms. So I'm excited because I like this stuff. So we're going to talk about atomic structure and periodicity, so let's get right to it. We're going to start with podcast 6.1, electromagnetic waves. And electromagnetic waves basically describe light. You see, light is made up of electromagnetic radiation. Electromagnetic radiation consists of both a magnetic field and an electrical field that travel or propagate at right angles to one another. Kind of like this. It was like the day Hunter had gloves on and he was directing our movements for an electric wave and our molecules moving around. Let's look at the parts of this wave. First of all, we have the wavelength. And the symbol for wavelength is called lambda. It's like an upside down Y. Wavelength describes the distance from peak to peak, or valley to valley, trough to trough. They're called the crests of the wave, right? So the top is the crest and the bottom is the trough, and the distance from one crest to the next is called the wavelength. The distance from its resting place to the top is called amplitude. So we would take half the distance from the trough to the crest, and so that would describe, like, from its rest position, how far it moves up or how far it moves down. Now, in a sound wave, amplitude could be described as like the volume of the sound. When you're turning the sound up with your remote control, you're increasing the amplitude of the sound wave. The wavelength, on the other hand, has more to do with the pitch. You see, if the wavelength is smaller, then the number of waves that could pass through a given point in 1 second is going to increase because we have smaller waves. That's what's called frequency. And a higher frequency sound has a higher pitch. So a low pitch has a long wavelength, and a high pitch has a really small wavelength. That's my frequency demonstration. You can play around with your own frequency. We measure frequency in kind of a weird unit because basically what it is cycles per second, and calling something just per second or second to the -1 seems weird. So we named this hertz after, of course, some scientist who was able to describe frequency in a way that everybody else could understand. 1 hertz is equal to the number of cycles in 1 second. That's the frequency. And for light, there's usually a lot of cycles per second. So here's an example of frequency. You can look at a longer wavelength, like this one, compared to a shorter wavelength like this one. In the same distance, having more waves passing through that same distance would describe something with higher frequency. And if you would draw a wave, then you would be able to see that when you have a higher frequency, you also have more energy. So let's start here and draw like a nice easy wave. And then I'll draw a wave that takes me a lot of energy to draw. Ready? Yep, that would have a lot more energy. It looks like scribbles. It's not scribbles, it's a wave. Yes, see, a wave with smaller frequency has a wave with higher frequency has smaller wavelengths, and thus it has more energy, right? It carries more energy with it. So that's important to understand the connection between frequency and energy. In fact, it's so important. I want you to go to this simulation that's online, and in this online simulation, you're going to get to play with the properties of the wave on a string. And it's really cool, but it also helps you understand how waves work. Waves allowed scientists to describe things about atoms that they were never able to describe before. You'll need to know what order they go in. Every type of wave is going to have a different wavelength, lambda, and a different frequency, nu. It looks like a V, but it has this curvy arm. That's the Greek letter nu. So here's all of the spectrum for the electromagnetic waves. The lowest energy with the longest wavelength would be radio waves. And then as we increase the frequency, we would build up the energy to microwaves, infrared, And then visible light, this is greatly exaggerated. Visible light only goes from about 760 nanometers to maybe 400, 380 nanometers, and that's the light that you can see. Higher energy than the purple color would be ultraviolet, then X-rays, and then gamma rays. So you need to know the order that these go in. So do whatever you got to do so that you can remember gamma rays have the most energy, radio waves have the least energy, and of course you got to know everything in between. You probably already have the rainbow order down, where red is the lowest energy and purple is the highest energy. But now let's fill in all the rest. Radio, microwaves, infrared, UV, X-rays, and gamma rays. And of course, visible light is the only part that your eye has the ability to detect. And we still have rainbow order as Roy G. Biv. Good thing you learned that a long time ago, right? So now let's look at the speed of light. Light always travels the same speed in a vacuum, and so that makes it pretty handy because that speed is constant. So we use the letter C to represent constant. The speed of light in a vacuum is 2.998 times 10 to the 8th meters per second. For most of the calculations that we're going to do, though, we're going to use 3 times 10 to the 8th meters per second because that level of precision will do for what we need to talk about. We also know the speed of light is proportional to wavelength and frequency, where the speed of light is always the same. So as wavelength increases, that means frequency must necessarily decrease in order to keep this number the same. On the other hand, if the frequency is increasing, then what does the wavelength have to do? It must decrease so that the speed of light remains constant. So these are all related to one another, and if you know the wavelength, then you can calculate the frequency, and if you know the frequency, you can calculate the wavelength. So we're going to do an example just like that. Example 1 asks, what is the wavelength of light? So we're looking for lambda that has a frequency of 5.89 times 10 to the 5th hertz. So here's how we would set that up. We know that C is equal to lambda nu. We're trying to solve for lambda, so I'm going to take the equation and C divided by the frequency ought to solve for lambda. So now let's put in our numbers. 3 times 10 to the 8th meters per second divided by 5.89 times 10 to the 5th. And that's hertz, which is 1 over second. So seconds is in the denominator both on the top and the bottom, so that can just go away. And you know what? When I did my calculation before, I got 509 times 10 to the minus 2 meters. And I think I used 2.998. I didn't round to 3. So if you're getting something different, then it's probably just the rounding thing. Let's move the decimal over. So 5.09. Left makes it larger, so just 5.09 meters is the wavelength. Put a box around it because that's the way I like it. You got it. Let's do another example. In example 2, now we're trying to find the frequency of blue light that has a wavelength of 484 nanometers. So we're still working with this same equation, but I've got to be careful here because the speed of light is in meters per second, so I can't put nanometers in that same equation. So I'm going to take the speed of light, 3 times 10 to the 8th meters per second, and I need to now divide by the wavelength in meters. So here's the shortcut I use in my calculator. Take 484 in your calculator times 10 to the minus 9 meters. Because a nano means -9. It's a billion nanometers in 1 meter. So we just put that in there. It's okay to put it in your calculator this way because it's easy, for one. And for another, this isn't your final answer. You don't have to worry about proper scientific notation until your final answer, right? So let's see, when I did this math, I got 6.19 times 10 to the minus 4 meters. Is that what you're getting to? That's what I got. So that's the frequency. No, that's not right, because it can't be in meters. Frequency is not in meters. Meters cancels. It's in hertz. And that just doesn't sound right to me. So let's take a moment. Okay, I went back and double checked my math because that just didn't sound right. For frequency, I should have a big number, and I do. For blue light, I have 6.19 times 10 to the 14 hertz, not minus 4 meters. But you see, it's a good thing that I had an idea of what 10 to the 8th divided by 10 to the minus 9 ought to be. Otherwise, I would not have caught that mistake. So always be prepared to do some mental math and estimations and make sure you're doing it right. So where did all these things come from? In 1900 or so, thereabouts, matter and energy were seen as fundamentally different from one another. It was thought that matter was made up of particles called atoms, right? And energy could come in waves. And the two were thought to be distinctly different, fundamentally different, so different that they couldn't be the same at all. But Max Planck was a German scientist who found that as the cooling of hot objects could not be explained by viewing energy as a wave, he began to describe energy as possibly made of particles too, that there would be some particle associated with energy. And this is his research. He found that the energy changes would come in chunks with a predictable magnitude. So remember, Planck was the guy with the photoelectric effect. We had this sheet of metal, shine a light on it, and what happens? I sure hope you remember this by now. You get electrons to flow. When the light shines on the metal, electrons flow, and we measure the current in amps, the electrical current. So he was able to see that not just any wavelength would do here. It was a certain amount of energy, not just any old energy. So that was the photoelectric effect. And then he could predict how much energy it would take for moving certain electrons. So he came up with this equation that the change in energy corresponds to some integer n times this constant times the frequency. That the energy was related to the frequency according to a stair-step kind of a graph. So it wasn't a gradual increase, it was up, up, and not anything sort of in between, just the stair steps. So n would be some integer, some whole number. And h is what's called Planck's constant. That was the slope of the line that kept coming up again and again. Planck's constant is 6.626 times 10 to the minus 34 joules times seconds. And you're going to see this number come up in a couple of different equations. So it's printed for you on your equation sheet. You don't have to memorize it, but by the time we're done with this unit, you might know it by heart. So these packets of energy are called quanta, which is the plural form of the word quantum. A quantum of energy would describe a discrete amount of energy, right? Because quanta means amount. And so that amount of energy it takes to get those electrons to move is this little packet. Now comes along Albert Einstein with his ideas about energy and relativity and how energy is related to matter. So he defined the quantum as a particle that he named the photon. Photo being the prefix that means light. So a photon then would represent like the particle form of energy. And he said that each photon has some measurable amount of energy that is, just as Planck said, Planck's constant times the frequency. And then we'll combine this with his most famous equation, E equals mc squared, which relates matter to energy. How are matter and energy related? Through this equation right here, where E represents energy and m represents the mass. So we can get to the mass of a photon, the apparent mass of a photon, according to this equation. So let's see how we might combine these two. Check it out. If we know that energy is equal to h nu, and it's also equal to mc squared, then I'm going to combine these two together. Frequency is related to wavelength in this way, that speed of light is equal to frequency times the wavelength. So far, so good? Great. So then I can rewrite frequency with the speed of light in it. And I'm going to do it this way. We're solving for frequency. Divide both sides by lambda. So now in the place of frequency, I'm going to write speed of light over lambda. And that's equal to this famous equation, mc squared. Let's solve for the mass now. Divide both sides by c squared. And I get one of my c's to cancel. And then lambda's already in that denominator, so I have h over c lambda is equal to the mass. And that's what we get for the apparent mass of a photon. So the big question is, which is it? Is energy a wave like light, or is it a particle like a photon? The answer is yes, it's both. This is known as wave-particle duality, and it describes part of the fundamental nature of not only energy, but also matter as well. So, in other words, energy has the ability to exist as both a particle and a wave. For that matter, everything that the world is made of can exist as both a particle and a wave at the same time. So, is matter a wave? Of course, because everything that the universe is made of has this dual nature, waves and particles both at the same time. Let me show you what I mean. So here's some evidence to show you that waves and particles are really the same stuff. It's the diffraction patterns. So when light passes through or reflects off a series of thinly spaced lines, it creates a rainbow effect, like a prism, right? And the waves interfere with each other once they move through the thin lines, and it causes the white light to disperse so that what you see is a rainbow. Well, what if we don't have white light? What if we just have any old wave, right? Then when it goes through a slit like this, it comes out as a curve on the other side. That's what waves do. So what if we have a barrier that has two slits in it? Now let's pass our wave through this barrier. What do we get? We get two curves. And those two curves interfere with each other. In this spot here, where they're both touching, that's where the wave crests add together to make a really big wave. But then there's other parts of this wave where they would subtract, and so we get an interference pattern that's very predictable. The crests add up where they touch. So if we have several waves, then we'll get several curves coming through, and where they're touching, they add up. But where they cancel each other out, it adds up to 0. And so this interference pattern is very predictable. For the double slit in the barrier, we're going to see the same pattern every time. Think about throwing a rock into a pond. You get this sort of circular ripple effect. Well, you see the same kind of pattern every time you do it, and we can predict what might happen. So let's talk about what an electron will do. It has mass and it has volume, so it's described as matter. So the particle can only go through one slit in that double barrier. So let's draw our barrier. We have two holes in the wall. So a particle, like one of you guys in my class, a particle could only go through either this one Or through this one, but you got to pick one because you can't go through both at the same time. What about a wave? A wave can go through both, right? It approaches the barrier, then comes out as a double curve on both sides. An electron does which one? What do you think it's going to do? Well, when an electron approaches this barrier, it goes through both, the same that waves do. And it makes an interference pattern the same as what waves do. So when you take an electron individually, it behaves much like a particle does. But if we look at the sum of what all the electrons do as a whole, they behave as waves. So how do you look at an electron just individually? We just don't. So here's a picture of what it looks like if we concentrate on individual electrons. So I've sent the electrons zooming through this barrier and they've collided with something behind it so we can see what's the pattern. See, the individual dots represent individual electrons. And as I send more of them through, I get more dots. Looks like particles, right? But let's keep sending more electrons through and more electrons through until suddenly appears the diffraction pattern that we recognize from waves. Okay, so in class I'm going to let the scientist who did this experiment explain his findings to you, but this video won't play on the Mac. So we'll have to watch it in class, and you'll see as the particles build up, it makes this diffraction pattern. So we see matter as a particle, but matter also has wave-like behavior. So de Broglie said that the wavelength of any object is proportional to Planck's constant and inversely proportional to the momentum. Momentum being the mass of the particle times the velocity of the particle. So we can calculate the wavelength for any object, whether it's made of energy or made of matter. We can calculate its wavelength because it's going to be proportional to its mass times its velocity. A larger particle has a wavelength that's too short to notice, too short to be able to measure, as predicted by de Broglie's equation. So let's do an example here. For instance, we know, let me clear my writing, there we go. We know that there's a relationship between wavelength and frequency. So let's work this one through. What is the frequency of the light with a wavelength of 7.8 times 10 to the second meters? So I'm going to start with the speed of light, 3 times 10 to the 8th meters per second. We're going to divide by the wavelength, 7.80 times 10 to the second meters. And my speed of light is never going to be my limiting factor for sig figs, because you know this comes from more sig figs than this. We're just going to only worry about what we've got for wavelength. So 3 times 10 to the 8th divided by 7.8 times 10 to the second. That gives me a frequency of 384615 meters, no, hertz, because it's frequency, right? So let's round this to, this number has 3 sig figs, so 38500 and one more 0 hertz. So 385,000 hertz would be the frequency of the laser light of a CD player. So now the question says, what is the energy? Let me move my writing out of the way so we can see the question. What is the energy of a photon of this light? So we need our energy equation. Energy is proportional to Planck's constant times the frequency. Well, isn't that handy how I already have the frequency stored in my calculator? 385 times 10 to the third hertz. And of course, I'm not going to round that in my calculator. I'm going to multiply that by Planck's constant, 6.626, whoops, missed a 6 there, times 10 to the minus 34 joules times seconds. And remember, hertz means 1 over second. So look, seconds is going to cancel, and I'll have energy in units of joules. That makes sense, right? We're used to seeing that. So multiply your frequency times Planck's constant, and I get 2.55 times 10 to the minus 28 joules. That doesn't sound like a lot of energy, does it? But that's just like one photon of light. Okay, what's the next piece? What is the apparent mass of a photon of this light? Okay, apparent mass. And we just got this calculation. It's Planck's constant times frequency, speed of length. What is it? Sheesh. I'm peeking at my cheat sheet. There we go. The apparent mass is Planck's constant divided by the speed of light times the wavelength. So 6.626 times 10 to the minus 34. And Planck's constant is joules times seconds. And we're going to divide that by the speed of light, 3 times 10 to the 8th meters per second, times the wavelength, which was it's right there, 7.80 times 10 to the second meters. Okay, now this is going to work out to give us units of kilograms, because 1 joule is equal to 1 kilogram times 1 meter times 1 meter per second squared. So that's what a joule is equal to. Meters per second cancels meters per second, and then this joules times seconds cancels our other second down here. Meters cancels meters, and we're left with kilograms. All right, time to do some math with my calculator. So what can I do here? I have energy, so I'm going to take Planck's constant, divide by the product of the speed of light times the wavelength. So I end up with an apparent mass of my photon of 2.83 times 10 to the minus 45 kilograms, where the mass of an electron is approximated at somewhere in the range of 10 to the minus 31 kilograms. A photon is significantly less than that. So a photon, if you could ever come up with a way to actually weigh this, you'd probably be one of the most famous scientists ever. You win a Nobel Prize, then you're going to share it with me, right? Of course, since I was your teacher. All right, well, you don't have to. The next one says, what is the energy of a mole of these photons? Of an entire mole. Well, we know the energy of one of these photons, right? We just had that answer up. So you know how many particles there are per mole, right? So this is a simple T-table type of question. So the energy of one of these is 2.55 times 10 to the minus 28 joules, and that is per photon. For every photon we have, we get that much energy. And there are 6.2 times 10 to the 23rd photons in 1 mole of photons. So I'm going to take my really tiny number for energy, and I'm going to multiply it by my really big number for moles. And I want to get all my digits in here so I don't have a rounding error making a mistake. So the energy for 1 entire mole is something more recognizable as significant amount of energy. I get 1.58 times 10 to the minus 4 joules for a mole of photons. All right, I think we have one more. Oh no, that was it. We have another example though. What is the wavelength? So let's see what we're asking here. Oh, de Broglie is coming up now. Remember, de Broglie said that the wavelength is inversely proportional to the momentum of our particle, the mass in kilograms times the velocity in meters per second. So that's going to help us find the wavelength of an electron with a mass of really tiny. Let's see. Let me finish writing Planck's constant before I start saying other numbers and it messes me up. That's joules times seconds. Remember, joules is kilogram meters per second times meters. Meters per second squared times meters. So we have Planck's constant on top, and on the bottom the mass is 9.11 times 10 to the minus 31 kilograms times the speed, 1 times 10 to the 7th meters per second. So it's approaching the speed of light, right? If the speed of light is on the order of 10 to the 8th meters per second, this electron is going pretty fast. So let's do this math on our calculators. And I get a wavelength here on the order of 7.27 times 10 to the minus 11 meters. So it's not in the range of visible light. It's a little bit shorter wavelength than that, a higher frequency. So maybe this might fall in the range of UV or X-ray, somewhere in there. I'd have to look at the spectrum to be sure. But it's more energetic than visible light. But let's solve this part. What would you calculate the wavelength of a softball to be, where the softball has a mass of 0.1 kilograms and it's moving at a pretty good speed, 125 miles per hour? That would be like a deadly fast pitch. Holy smokes. From a softball? Phew, that one got launched. So let's take Planck's constant, and we're going to divide by the product of mass times velocity, even at this incredibly high velocity for a softball. 125 miles per hour. Wait, I can't put miles into a physics equation. All right, we're going to have to do a t-table. 125 miles per hour means miles is over hours, right? And a 1600 is a mile, so 1 mile is 1600 meters. If you've never had to run a 1600 for PE class or for track, then you've just missed out on an important experience of childhood. So now I have meters per hour, and I want meters per second. So I know in 1 hour, there's 3,600 seconds. Now I'm going to get to meters per second. So let's take 125 times 1600, and then we're going to divide by 3,600. Oops, didn't quite get there. And I still did it wrong. Okay, I get 55.555555, so 55.6 meters per second. That's what's going in here for speed, not 125 miles per hour. Now we got something we can use. So Planck's constant divided by the product of mass times velocity. And I get a wavelength that is 1.19 times 10 to the minus 34 meters. Well, there's no way that we could actually measure something with a wavelength of minus 34 meters. We can measure something with a wavelength of minus 11 meters, but minus 34, that's too small to measure. It's not too small to exist, but it's so small we can't measure it. So we're going to be drawing waves in class, and you'll get to see what it means to have a really, really tiny wavelength. What does that mean for us? But I think that's it for this podcast. Hey, I was right. So the next time I get to see you, we'll be in class together working this through. Catch you later, guys.